So great, such a lot of people show up here today for our topic. Maybe a few words in advance. So while Rudy, Thomas, and me will, so to speak, share our experience on how we could probably bring art into the enterprise. This is not an IBM venture, so to speak. This is our community meetup. So don't expect any IBM advertising or anything of that sort. Of course, we did use some IBM tools for putting up to the demo, but that could also be, bought or get from Amazon or Google or whoever. We use only open source software. By the way, also now IBM Cloud, there's a lot of open source software anyway. So nothing is special here about IBM. It's just about what we think, how we could bring R into the production and experience and share that experience. Yeah, but on the IBM side, I have to make one announcement that we have on March 18th at 1700, right here, a meetup on Devops. And yeah, so you're welcome to join that one too. There is flyers lying outside there if you want to get the details. All right, so then, yeah, let's jump into the topic. That should work, no? So I have one slide to present, so I will cover the agenda for today quickly. So the first thing is we start off I've been studying data engineering and statistics on the Technical University in Vienna, so I had really the pleasure to do so for a couple of years while working parallel to standard work. So what I learned there was doing statistics with R. My general working equipment was a laptop. I was always keen on getting all the data on my laptop, writing some code, putting out maybe some reports. At the times it got more organized. I put my source code into a repository, learned how to write R packages, get it some versions. Then later on, write reports maybe in Jupyter notebooks, but that was essentially what I could bring to the client. You give me the data, I do some analysis, and then you get a report on what you about your data. But this will essentially not work out in a professional environment. You have to bring your R code into the pipeline that the company is working with, intercommunicate with the rest of the services, be a service that can be consumed by different people. So this is quite a different setup from what I at least was used to a couple of years ago. Now, as soon as you enter the enterprise, you will probably meet a world that's totally different from that you used to work in. In particular, the first problem usually is that you have difficulty getting to the data in the first place, because they are provided sensitive data that you cannot easily address. So this is a couple of things that right from the beginning will give you a bit of a headache. In addition, you will find processes like demand management, test management, release management, but also incident management and so forth. So a lot of things that most of us probably will not be used to. Now, on the other hand, the companies themselves, maybe they just make the beginning of their journey with AI or for machine learning in general. So they will also not be ready to adapt to the kind of work that we need to bring to them. So this will essentially be also data-centristic work. And so some of those problems that show up there, Rudy Peiler, our architect, he will report on a couple of things that he met when talking to clients that have data science related projects. Now in the second part, what we will want to do is the CRISP-DM model will guide us through the rest of the session, so to speak. The CRISP-DM model describes essentially the way from the process between the data scientist and the business. So that model is very much focused on how a data science project is being set up and how it relates to the business such that the business goals are being met. And we will use that as a workhorse to guide us through the rest of the session. What we essentially will do, we take the core part of this CRISP-DM model, and that is the modeling process. So from the ingestion of the data, the preparation of the data, the development of the model, and then going to production. So this is the technical core. We will try to pick those and forge an application out of these technical parts of the CRISP-DM model, and then so to speak, that covers the whole process of a machine learning project from data ingestion up to into production. And what we will try to demonstrate is how that can actually be brought into production with a little demo that we will show at the end of the session. Yeah, so this is our topics for today. And yeah, I would like to ask Rudi to start out with bringing some of the news from the enterprise. Thomas, du müsstest jetzt kurz umschalten.
Ich nehme das. Yeah. Okay, hello. Welcome to the 13th floor of IBM. I hope you have a fantastic time here. I will talk a little bit about what it means to bring machine learning algorithms into production. So, to start with the feeling of our customers, they all want AI. It's a cool topic. We prefer to talk about machine learning, but essentially it's more or less the same. So 85% say, yeah, cool, let's do it. But there's a big but. Our customers, they see two main issues. The first is regulatory complaints, it's compliance. So usually the data we require to do our work is the most essential data of the customer. They don't want to have external companies easy access. For example, we've been working in the banking environment, working on, for example, fraud detection in payment systems. So if you have a look at all the payment transactions of a bank, this is rather sensible data, and it needs some kind of convincing work to get this data in your hands. The second one is the technical skills. We see that in many of our customers, there's not sufficient knowledge and sufficient capabilities to even execute machine learning projects. So one of the things we often see is that there is a clever guy or a girl with a Jupyter notebook, some impressive code, algorithms, and as soon as the algorithms are there, problem solved. But there's this data science, there's this data science knowledge or this mathematical statistics know-how that is one part of the team that you need, but you also need people that know a little bit of IT, in particular regarding large data sets. You need the buy-in of the business people, of the subject matter experts, where you want to solve some problems, and this Venn diagram by Drew Conway is not implying that this is one person in the middle, but this is a team effort. So in order to succeed in the enterprise environment, you need teams that have skills in all those areas, and the intersection will give you success in your project. So coming back to the Jupyter notebook, the machine learning code actually is a really small part, and you have to do a lot of other code, of other systems, of other configuration around this machine learning code. And that's the trivial truth of doing machine learning projects. And this is the reason why we thought that it's an important topic that we want to talk about, and also to give some practical hints how to solve that. Because when we started to have a layout or an architecture of our system that can fulfill all these requirements, We saw that we got nodes after nodes after nodes after systems that we all need to interconnect, to configure in the right way, so that at the end you have an enterprise-grade machine learning system. So this is, I think, this looks rather trivial. You need to somehow get the data and govern the data. You need to somehow develop the models. You have to do versions of your models. You have to deploy the correct version of your model. You want to monitor your system, whether it performs to the specifications that you wrote down. And then there's the feedback loop that perhaps your customers or your clients tell you that maybe there's room for improvement, and you start from the beginning again. And the talk today is exactly about this circle of development. And this is not static. It's a dynamic environment, and some nerves are required to stay calm during such a project. This is just a short view. So we at IBM usually deliver projects in an agile way. This also should reflect that it's not static, that it's a dynamic environment, that the requirements are changing, that your understanding of the problem is changing, that you need constantly do loops, talk to your customer, find out what the goal still is, if we're still on the same, going all in the same direction. You need to talk to a lot of people. And this is just a little diagram to give you an idea that around your agile project, there are a lot of people that want to influence it, that want to be informed, that you have to talk to. So it's a lot about drinking coffee. High caffeine resistance is something that you need for such projects. In particular, I want to point out that you have to somehow align with the enterprise architecture, vision and goals. You have to really understand how operations is working, and we have the term MLOps, machine learning operations, for that. So it has to be scripted, it has to have automatic regression tests, it had some kind of continuous integration, continuous deployment. This is the standard for normal software development, and for sure it's also a requirement for machine learning projects. And data governance, I want to go a little bit deeper into that. We had on the first slide, we had this mentioning of compliance. And we see that in the environment we are working for, the General Data Protection Regulation, but also other laws like in Austria, Bankwesengesetz, Telekommunikationsgesetz. So laws and regulations about how to deal with data. We have to comply to them. For a company, there's no way around it. And then you have general security and data protection considerations. And the first thing you need for a data science project is data. And when you go to your customer and tell him, I need your data and I need your production data, and I don't need 20 examples, I need about 1,000 or 10,000 or 1 million, then they start telling you, I have to talk to my security officer about that. And the first thing you would hear from the security officer is, no way, no way. You will never get to that data. And then the real fun starts. So one of the first things we usually do is a data anonymization or pseudonymization project. So we work together with the customer to find out what are the most protected values that perhaps for the machine learning project you don't need to have a look at, but to somehow scramble it in a way that you can still do your mathematics, but that you can immediately trace the data to a real person, to a real bank transfer, and you can talk a long time about how much aggregation is necessary to really get anonymous data sets. This is not trivial. I saw recently, for example, a talk about Amazon. using artificial intelligence to selecting new people, to recruit people. They were, of course, aware of bias. We talked about not too many women in IT, so they said we want to be an equal opportunity company. So they removed the gender of the data. Nevertheless, the AI learned from the data to prefer men because there were things like in the Vita you found the women's college of somewhere. So already in the name of the universities where females studied, you have bias, and the artificial intelligence learned that from the employees that Amazon had at that moment, that was the training data, all the females that studied at the university that was particularly targeted towards female students, they were simply ruled out because the AI said that's not the target. So you have to be very careful to have also substantial evidence for bias, not only the direct, but we know, okay, remove the gender. It's not, maybe not enough. And also, I mean, things like encryption or audit logs, you have to cope with that. So keep that in mind. That's the reality out there in the market. For data governance, so I think that we spend 80% of our time in machine learning projects in extracting and also anonymizing, transforming and loading data somewhere. So this is rather cumbersome work. It's not as intellectual challenging as doing real algorithms, but the truth is this will take most of the time of your project, just to get the data in a format that you can ingest it then in your algorithms. And in order to understand your data, you need to set up some kind of metadata repositories, to have an idea, to register the data, to discover it again, to share it. So if it's not a one-person project, but you have several people working on it, so they have to find the correct data, to versioning data sets. In particular, if you're talking about really large data sets, versioning is expensive and it's not trivial. And also to find out where the data comes from. So this provenance, lineage of data is something that you have to keep in mind, because at the end you have to prove that your machine learning project comes or has trained from exactly that version of the data. And yeah, access control should be there as well. Not everyone should see the data. We heard that it's rather difficult, or the sensible data in there. So there are, of course, packages out there. I named a few. So it's Airflow and Pachyderm are open source packages. And I think this is the only advertisement that we have on the slide about IBM. And this is the end of my part. And I will hand over to Thomas.
Okay, Rudi, thank you. So, couple of lessons to be learned here. The one thing I would remember is that we need to be compliant, in the sense that, for example, predictions that we make have to be maybe subjected to compliance checks. So we always have to make sure that we know which data our prediction is based on, which version of the model did the prediction, and what the eventual outcome was. So yeah, another view of the company. You see a lot of boxes there. A lot of things that in a standard company are being used that you will be confronted with. So in particular, software pipeline often starts on the demand management with Jira Confluence. You have a whole testing unit usually that cares just about the testing of software. Also, you have the test data management, the data management in general. So there's a lot of things that a lot of people you will have to interact with. We will try to cover part of the topics here. Obviously, the pipeline will be something that's very interesting for us because we want to make more or less an automated machine learning application. Testing will be something that's of course important, and the data themselves naturally also something that will be covered here. But first, back to our workhorse for this session. That's the CRISP-ML model. Yes, it describes the connection between business and the data science, not in the steps only, but also in a more depth. It describes which documents have to be provided at which stage, which people you need at which stage, what deliverables have to be constructed, and also how you make sure that the progress of the project follows certain parameters. And you will, at each stage in the project, you define what makes the project successful or does it not make successful. So this is something that, this is more or less a way of living the data science project. So this is something that you can bring into the enterprise. We have used it successfully before. So this is something where you can say, okay, we start out on a well-planned way. We deliver projects, we deliver documents. You're completely informed of what is happening. We white box, so to say, what we do. We're not doing the black boxing where the data scientist goes to the laptop, hacks in something, then there's some outcome. No, all the time, everybody in the project that you talk with will know what you're up to and what is happening. If we look at the core part, the technical core part of this of the CRISP-DM model, then it's always the data ingestion, it's the data preparation, it's the feature forging, it's the model training, and the model storing, and eventually verifying how the model performs and putting that model into production. We can roughly, presumably, differentiate in two phases. The one is the training phase, and the other is the scoring phase. So the training phase where you create the model, and the prediction phase where you actually make the predictions then. So this is what the company actually wants to consume then, and what gives the value to the company, that your prediction is doing something that it has been asking for. Now, so this also gives us a first glimpse of what the application, or how the application needs to interact with our system. So in the first phase, we'll probably also always interact with the data. Of course, as Udi said before, it's important to get access to the data in the first place, but also it's important that we as a data scientist do not try to get the data on a laptop and then work on the laptop and not think about how in the production the access to the data will work. So the first step for us is that we will want to get access to those data with a technology, with packages, with our package that actually access these systems, so that what we ever eventually put into production works the same way as you do it in the development cycle. So this may be things like databases, data warehouses, could be file systems, may eventually be some data platform. So this is all different technologies that you have to think about how you will organize that access. The second part is the scoring. Obviously, there will be different types of scoring. One may be batch scoring. This is things that may be implemented in something like an R script, but you have to be ready that you get a lot of data that need to be scored. On the one hand side, on the other hand, of course, many people have like web shops or similar things where you will have to be ready. Hello? You still hear me? Okay, that's good. You'll have to be ready to score in more or less real time. So performance is a very important part of that, and we'll care about that on our demo. The rest of the part where you obviously also interact with a company, we do not talk about that much today, but of course it's very important either. So what our idea for today was that we try to operationalize the technical parts of the CRISP-DM model. So this is more or less a list of 10 or something interfaces that we thought taken together and implemented. These are the steps that we eventually will do anyway on creating the data science application, that we can take sort of an approach of class definition. So we define more or less a class of, we call it here CRISP-ML, and then we define a couple of interfaces that need to be implemented in order to make the full data science application. And So there is parts for the training, part for the scoring, and of course there's a couple of functions that will be used in both of them. Of course, the data preparation routines in particular will have some parameters that are established during the training session, but will of course have also to be applied to the data during the scoring session, so that the same, so to speak, data are being fed into the model during training and during scoring. So from our view, the application landscape would roughly look like we have a part of the training and we have a part for the scoring. They will interact with each other, presumably with a database or some other kind of storage. There will be information that needs to be passed from the training to the scoring environment, and maybe vice versa. Essentially, the training will then be organized by some sort of trainer. I call it the trainer here. And on the other hand, we have clients that will eventually consume our scoring. And I mean, if that is a package of R that contains all the routines, or you have where you on the one environment, the training environment, only call the part of the training part of the routines, and then have it, so to speak, with a different set of functions on the scoring area, that is more or less of a technical decision. But usually you will have a different server for the training than you have a server for the scoring, because the training needs to have a lot of CPU, a lot of memory, usually because the training is very intense on that part. On the other hand, the scoring server will presumably be configured totally different, because it needs to be fast if you have a lot of scoring. And yeah, so we also devised a little demo for that. We'll show that later on. We have a little shiny application that simulates the trainer, and we have a load test application that simulates the REST client, so that we can see how this model performs here. So this is something that we thought would, from the beginning to the end, implement all those methods that the complete data science or the complete machine learning model would require. So what you see here is exactly those method names that we have implemented for the demo. Yes. So data ingestion, the data preparation, the creation, the training, the persistence of the model. I mean, everything should be implemented. We only implemented part of it, but you get the idea when we show the demo. Now, what's the nice thing about this setup is that you really have the complete machine learning application. It's all under version control. It's a complete thing. You will devise it in the development environment. You will presumably package it with an R package. And then the whole thing can be deployed to any of the testing environments that the enterprise may have. So the advantage here is that also the creation of the model already is being subjected to whatever the company wants to have as quality assurance process, documentation, whatever. So this is a bit different from other scenarios where the model is being created in an area with in the training area, where there's a data scientists working, specialized people working, they do some magic, and at the end of the process, they have the model, they put the model into the model registry, and then comes the production picks the model, and then, so to speak, goes online. So what we try to do here is pull out the magic of the creation of the model, and it also makes the subject to the quality process. This also has another advantage. We've been talking, Rudy has been talking a lot about how we get access to the data. I mean, we could easily see that, for example, in a development environment, we will not have a lot of data because simply we don't get it. So whatever model you devise in a development environment, that will not be a good model. If you go to the quality environment, in many companies you there have anonymized data that people are allowed to see. But again, if you make your model based on these, this will not be the best idea. So what you need is production-grade data to devise your model. And with this setup, you would essentially make sure that the creation of the model is being subject to quality criteria. You would know that the way that the model is being built is essentially one that you can trust on. If it's done blindly, without interaction, apart from some quality criteria, of course, that are being generated automatically, like precision recall or whatever you would like to have there, and then could bring that as a whole thing into the production. So this is the general idea what we thought we would try to follow for a while and see how it works out if we could use that as something that we could bring to the enterprise. Yeah, so maybe one more thing. So this is really then, you can put it on one box. You have one R application, you instantiate it on one box, and that will be more or less your portable machine learning application. There's a couple of interfaces that can be called to all of what the machine learning needs to do. Oh, wrong direction, sorry for that. So yeah, what we did then is essentially try to build a demo application for this platform. So on the one hand, we have the server that actually does all the work of the creating the model. Then we created a little console. It's a Shiny application, very primitive Shiny application. Don't look at it. We'll try to hide it because there's a lot of people who can do a lot better here. But nonetheless, that Shiny application has the task of invoking the REST services that we eventually implemented for those data science for the data science pipeline. The advantage is this is more or less can be deployed to any runtime that you would like to do. Of course, it runs anywhere where R would be running. In our demo, we'll try to do something a bit fancy. So we deployed it onto a Kubernetes cluster on the IBM cloud, but of course you could, as I said before, run it on any cloud you would like to. Yeah, so we now have more or less this service architecture. We know the software that we want to implement, and what we want to now do is something that is not so oft found in traditional environments or traditional companies, but we wanted a bit of fun also, so we tried to implement a demo with some new technologies based on DevOps and MLOps and automation. And yeah, so Thomas is our expert for the DevOps stuff, and yeah, he will give us a bit of a heads up on what DevOps is all about.
Yeah, hello. A few words on DevOps from my side. What you see here is a visualization of a traditional software delivery lifecycle with a sequential step-by-step approach where the demands come from the business owner over the planning and the requirements analysis through the development, test, and finally we have the demand in the release manager, which plans the deployment together with the operations team. And finally, it gets to production and ends to the customer. Mostly all these different areas are represented by different teams, not well integrated to each other. So you have a lot of communication effort in between the teams. And overall, it brings you a lack of time to market possibilities in your project delivery flow. How can you improve that? With establishing agile methods and DevOps. Agile methods, especially in the area of planning and development, and further on, you have to establish DevOps practices in the integration between the development teams and the operations teams. Overall, the goal is to have a continuous flow and a continuous integration over all these areas, again, from the business owner till the customer. What do I get out of DevOps? Agility and flexibility in my software production lifecycle. Standardization with DevOps is a lot about optimization, and I need standardization with a high degree of reuse in my project. Fail fast and fail early. When I apply continuous integration and deployments to all my stages, I will recognize errors early in my project phases, and automation overall improves quality in the way I produce the software. What we see here is our general view on DevOps overall. In the center, with the green circles, you see the general software lifecycle from steering over development, test, the deployment, and the operation. All these areas with a continuous feedback integrated. How can you support this lifecycle with DevOps? There is 6 practice areas around them, from continuous business planning, collaborative development, continuous testing, where test automation has an important role to it, continuous release and deployment, where pipelines and tools for it support the process, continuous monitoring, where a central logging and auditing platform is essential to provide to all the team members, and finally, continuous customer feedback and optimization with feedback on our system performance metrics, and also customer feedback on the systems, which can again be used as input on the continuous business planning to decide on further improvements of our software, plan the next release cycles with it. Overall, these practices, we see 3 dimensions consisting of the people dimension, processes, and technology. In the people dimensions, you have topics like the organization and also cultural aspects. Often mentioned topic is this so-called Devops culture, which is an important topic when it comes to DevOps between the teams as well. The processes dimension has all the processes part where it needs to support agile methodologies, especially in companies with a long history of software development. There is existing processes, and you need in a DevOps transformation also an adoption of your processes. And finally, the technology dimension, where we see all the technical aspects and tools needed to support the 6 practices in the DevOps area. A successful DevOps transformation will only get done if you consider all these 3 dimensions, people, processes, and technology. Further on in this session, we will mainly focus on the technology aspects. Yeah, some more principles on DevOps. Continuous everything is one of the key topics in the life cycle. With DevOps, collaboration for speed. It's important to break up the borders between the teams, have a collaborative steering with an end-to-end view over the whole production life cycle, feedback loops between the teams, to be able to react on issues in an early stage. Dashboard everything. Today there is perfect tools available to provide dashboards on all kinds of information needed in your delivery cycle, and it's an important topic to bring visibility to the teams. Automate everything, continuous delivery, continuous integration is a prominent topic here. Infrastructure as code can also be seen as an important topic, especially when you're on a cloud-based infrastructure. Test everything, as already mentioned, continuous testing, test automation should be a standard used in your life cycle. With test automation, you get early feedback of the quality of your software. As a cross-board around monitor and audit logging, a central topic, provide the logs and the audit logs in a central infrastructure to all the team members. Another points about automation is one of the the key points when it comes to DevOps. If someone has to do the same thing more than once, it's a candidate for automation. There is a good chance that you have to do it third, fourth, and fifth time as well. If something is hard to do it repeatedly. We all know that kind of works we are confronted with. For example, you can see here a kind of production deployment. I know situation where it takes weeks of planning and coordination to get a production deployment done. If you get it done in your setup, if you have to have production-like test systems and stages, if you get it done to get deployment automation, configuration management in your test stages as well, then it is an easy step to apply that practices on the production system as well. Yeah, iterative and frequent deployment also fits to the topic. Continuous monitoring as well. Key practice with DevOps. Yeah, finally said, all these DevOps principles also apply to MLOps. Needs to be considered on MLOps as well. MLOps practices and techniques to support the data scientist in the cooperation with the operations team. And as Thomas already introduced, CRISP-ML could be an approach to have an automated way to get that integrated.
Perfect, thank you. Okay, thank you. The one thing that I definitely take from this is, if it's hard, then do it repeatedly. So, for example, for me, it was hard to write R packages because I thought it was too complicated, or the syntax was too complicated for doing all these annotations. But this is something that I swear I will do repeatedly until it works and get it also done automatically. Now, so we have for sure this in mind when we put together our application. So we'll have these ML ops and DevOps principles applied to our application. So we'll be more or less built automatically. We'll show you in a second. On the other hand, what we also did is not build that application for the standard enterprise environment, for example, with Jira Confluence, maybe a Jenkins pipeline, and then into a VMware box or something. We thought we would try to do that into the cloud and try out the new technologies. So this is something so that we thought would be also well adapted for today. All the applications that we put together are Dockerized. So the Shiny application is Dockerized. We implemented the machine learning application with Plumber as a REST service. So also that is Dockerized. We did deploy that with a pipeline into the cloud. We'll have a look at that a bit later on. But first up, of course, this also goes then is Dockerized and goes to Kubernetes. I hope most of you already had the pleasure to make contact with Docker and with Kubernetes. There may be some not, so a quick wrap up of that. From our point of view, or from the point of this application, the Docker is just more or less a lightweight VMware box. It's a Linux box that is crafted in a special way, that is being run in a special way. But essentially it contains an operating system, or at least a part of an operating system, the rest provided by the host. And then with a thing that is a Docker file that more or less contains those steps that you do to install your application. And you would then persist your application as a so-called image that goes to an image registry. And from there it can be taken and then reinstantiated into what is called a container. The container is then the runtime of your application, like it would be in a standard system, a VMware box or whatever, or a Windows box, whatever you are running. But this is more or less, so to speak, a lightweight application that can be instantiated by a so-called Docker host. Now, this can be run on your laptop. This can be run more or less on Windows or on Linux. There is an implementation for all of that. But what we will be doing is run it on the cloud on Kubernetes. Kubernetes is an orchestrator for containerized applications. So, sorry. So if you have a lot of containers running, then you need an orchestrator. This is Kubernetes. So Kubernetes not only has the ability to orchestrate applications, but it also provides scaling. It provides load balancing. It provides log connecting and a lot of other nice things that part of those we will have a look at later on during the demo. So one of the important things for R is, of course, how do we scale R? I mean, R has the notion of not being too fast. It has the notion of not being scalable because it's single-threaded. I've been doing performance tests for several years in my life, of course not with R because that was long before I started to use R, but nonetheless, of course, we are very aware of this problem and we need to take care about that in order to get successful R deployment into production. Essentially, one can say that scaling in R may be divided in two different sections. The one thing is that what are the efforts of R itself on scaling? So there's a couple of methods that R itself provides to do scaling. The other part is that if you deploy that into the cluster, into the Kubernetes cluster, the cluster also provides some methods to scale. So of course, there's a lot of possibility to scale in R itself. There is two things I would like to point out or address or notice. That's the do multi-channel package that enables R to take advantage of processors that feature more than one core. So the multi-core processes will then fully be used if you use that package. It will take a bit of adaptation for the code because you need to use things like, for example, the for each package that essentially parallelizes the loops. Or you will have to use, for example, caret, where the hyperparameter tuning that you would use for model creation would also be something that can parallelize. The other thing that I thought is very interesting that I don't know a lot about is the parts where R is doing asynchronous application calculation. So this is the future and the promises packages that essentially will provide possibilities to start additional processes that then take on part of the execution and then return to the main program flow at certain points of time when these are finished. So this gives the possibility that, for example, a Plumber application can run part of the thing while caring for other connections. So very important, but I'm not too deep into that. Maybe we have a chance to dig into that a bit later when we really try to get more into details about the scaling. The other thing is the cluster itself can do scaling. So the one thing is it can start more than one node. So if you have a load balancer in front of that and you, for example, make REST calls, the load balancer will, so to speak, distribute the calls between the instances of your application. The other thing, it can also scale out automatically if you have a lot of, for example, CPU consumption, where you have a lot of connections concurrently active. Then you can teach the load balancer to inform the Kubernetes cluster that you are above the limits, and the Kubernetes cluster will then automatically start additional instances. So these are essentially the two things that we can use for scaling. The important thing is you should try that up front. So talking about automation, load testing is something that's extremely important to make sure that you really get the performance that you need then in production. So I've been doing this for several years in my career. It was always been quite a bit of fun. And the question now was, how would we do that in a Kubernetes clusters or in the cloud environment? Of course, we could still use gmeter for that, but gmeter is a rather, I would say, clumsy thing to operate. I've been using it for many years, but nonetheless, the scripts that they use, they're very hard to maintain. This is XML files, and who likes to program in it? So we were searching about for something that we could use instead of that. I came across the Influx Db and the Grafana. So the Influx Db is a database that essentially is a device to handle time series data, and this is exactly what we're talking here about. It interfaces nicely to Grafana. That's not only visualization, but also alerting tools. So you can, if you go above certain thresholds on the data, you can automatically create alerts. And Then this Influx Db is also, and that was an important part of the decision, readable and writable by the Influx DBR package. So you can write data from the application into this database and then visualize it in Grafana. But you also can read the data from the Influx Db database, so that the data that you have written there, you can analyze in any which one way that you would like to do. And the coolest thing about all that was that searching a lot for load testing tools, I found several of these. Of course, there's dozens out there. But there was a hint to one thing that I never heard before, that is load impact K6. The nice thing about that one is that the load testing scripts are written in JavaScript. I mean, I don't have any idea of JavaScript, but it's enough to do Steuerung C, Steuerung V. And there's a lot of people, of course, who can do JavaScripting. So there is people who can write the load test, and then I could execute that stuff. The nice thing about that is they provide a Grafana package, Grafana dashboard for visualizing their results. So as soon as you execute a load test with K6, they generate the data in the Influx Db, which can then be visualized in Grafana more or less immediately. So we also used it. So the CRISPR-ML and also the Shiny admin, they write into the Influx Db. So what we get here is data from the load test client, so their view on the response time. But what we also get is the view of the response time of the application itself. So we write in the application at the beginning, entry and exit in the function, and then measure the time that passes by in between, so they get to a response time at the same time also into that database. We will try to show that if we have enough time. I'll try to be fast. Yeah, so a couple of things. When writing the application, you have, of course, as already said, be aware that you will have to talk to a lot of different devices. The one thing that we try to emulate is an enterprise is using the DB2. That's easy to get in the IBM cloud. You have 3 clicks of a mouse, you have a DB2. But then, of course, starts the headache. You have to install the drivers. The DB2 drivers, not too easy. And of course, you also have to learn how to access with a database, but nonetheless, very important to do so. We use the ODBC package and the DBI package. There's one that we did not use, but that essentially should be on the agenda for talking to the database. That's the dbplyr package. This translates R code into SQL code so that you do not execute R code. You do not have to transfer the data into the memory, but you execute that stuff. Essentially, simple operations adapt to do that. You can execute these things directly in the database. The other thing is the pool package. If you talk to the database, it's always a good idea to get a database connection pool so that I do not establish the connections a lot of time, because this is always time. Yeah, so this is more or less something that we already used in our package. The other thing is about logging. Thomas already said that in the container and in the cluster, the cluster collects the logs for you, but you have to write the logs in such a way that the cluster can collect these logs. So this essentially means you must write the standard out. What we learned to not do, you will have to do again. You write the standard out. The other thing is you could probably use the syslog logger. There's a couple of packages in R that you could use for logging. But the syslog package is something that writes more or less into the syslogger. And the syslogger, again, can be configured from those log collectors in the cluster to read your standard log files, which is important if you have to log something, for example, in Shiny, in a reactive area. There you can, their standard out is being cached, so you can use standard out to do so. You could use standard error, of course, but nonetheless, this is an option where you could write additional log files in a standardized manner. The other thing is, it's always a good idea to know about your application, what memory you consume. And I must admit that this was something that I really still have a problem with. I only found 2 methods that would give me information about the memory that is consumed. The one is GC, that also does the garbage collection. The other is memory profile, coming out from the Java world in a way. Calling GC is strictly forbidden, total anti-pattern. You never must call GC from the application level, because the GVM knows when to do that. It takes a lot of time if you have a lot of memory to collect. And even if you don't have memory collect, just the passing takes a lot of time. So you must not do that. but the information that's in there is something that we would like to see. So I still hope that there is some package out there that would give detailed memory information that we can log. Then again to the Influx Db, and then have our plots about the memory consumption of the application. Yes. Yeah, so sysget is something that one could call, of course, but the interesting thing would be what is the view of the application. So how much memory does the application think it consumes and it still has available? So in Java, it's more or less easy to ask how much memory do you still have? There's another couple of things that we would like to monitor, like the couple of, like the number of sessions being active or similar things. Database connections, how many of these are open? Plumber, we would like really to know how many connections do you have currently active, how many are being served, how long have they been waiting, what's the length of the queue. So a lot of things we would like to know in order to be able to analyze the performance behavior of the components that we have. Yeah, so as I already said, automation, automation, automation. Thomas also said it. So that's really the important stuff. We do not want anything manual, any manual work. It's not reproducible whenever you touch the mouse or touch the keyboard. That's something that may be different the next time. So Thomas, please give us a little heads up on the pipelines that we set up. So this is the part, the last part of the things that we implemented. We will have a short intro on the way that the cluster is being set up and on the way that the pipelines, the automated build pipelines look like.
Yeah, a quick overview about the setup of our demo implementation. So all the services is hosted on IBM Cloud via standard services or open standards. The main blocks for this is on the left side, the IBM Continuous Delivery Service, where the tool chain is implemented. Within this delivery service, with the light version, you get a GitLab community edition with it. GitLab with the web interface, the Git repository behind it, and together with a GitLab issue management with it. In connection to that, in the pipeline, we used Tekton, which is integrated as a standard till a few weeks or months in the IBM toolchain. Pipeline is a perfect fit what we recognized, especially when you're in a Kubernetes setup. Tekton provides the resources via standard Kubernetes mechanism. The container images is a version that's stored in the IBM Cloud Container Registry. And the runtime is hosted on the Kubernetes cluster consisting of a master node and 3 worker nodes. Runtime of the pipeline with deployment to the demo application consisting of the admin part, the CRISP pods. As cross services, we are using LogDNR on the one hand side for application logging, on the other side for activity tracking, where all cloud activities is monitored, and Sysdig for monitoring and dashboarding. Yeah, here a quick overview about the build and delivery pipeline and how that fits together with GitLab and Tekton. On the right side, the Tekton definition of the pipeline, which is YAML files we version together with the application in the repository. You have a listener YAML pipeline and tasks YAML where the steps are defined. In the tasks. How is the pipeline triggered? You have a source code management system with GitLab and Git, a commit, or could be a merge request as well. Triggers the configured listener. The runtime itself is directly instantiated in the Kubernetes cluster with an instance of a pipeline run based on the pipeline definition, and further on a task run. The results are stored in the image registry and deployment of pods.
nonetheless, quick summary of what we put together. So you already know them. This part, so this is the application. As the trainer, we have the Shiny application. As the REST client, we have the load testing setup. Thomas just described the GitLab setup. And in addition, from the cluster, we have the collection of the log files. And we have the monitoring, the system monitoring from the cluster. So that is an overview of all the processes that run there. So we would like to make three short steps in the demo. The first is we would like to show you the application itself, show that you can click on it, which is really important because in the background we make these REST calls. So we click on our Shiny application, and this will make REST calls, and all the work will be done on the server, and we only pass back a few images or something like this to the Shiny application. So the Shiny application essentially has no access to the data. Yes, it's no access to the data. It has just access to what the server delivers, the REST calls. The next thing we want to show you is the pipeline. So I will change the title of the Shiny application, and in RStudio we'll press commit and upload. And Thomas, in the meantime, will show us then how the pipeline, like magic, starts to deploy a new version. This will take 2.5 or maybe 3 minutes if we're unlucky 4. And then we should see the new version of the Shiny application. And then what we would like to do is quickly start this load test. We can look at the Grafana dashboard, so we can see the response times from the application itself and from the load test client. I would then, in a first quick check, try to see if everything still works with one virtual user. And then we would switch to 2 virtual users and then see that the response time essentially doubles. And would then try to start a second pod, and we would then see that the response time somehow drops, but not in the expected manner. So there is still, so that it's not back to normal then, it's still a more or less crazy pattern that we will see, at least is what I saw. And we still have to investigate all the components of this load test setup, from the load test itself, via the Plumber, via the Kubernetes behavior. So this is then open to what we usually do when we do performance testing. We need to investigate. Dann schalte ich jetzt mal und du wirst dann quasi parallel herzeigen das Log-DNA. Ja, ich schalte mal auf meinen Schirm. Oh ja, fantastisch. Ah. Nein, was willst du? Was sieht man? So, ja, das ist Demi. Aber ich muss das da hineinfüttern. Was?
Geht das nicht?
Nein, das geht nicht. Weil ich muss da.
So.
Nein, das geht direkt da rein. Das war eben die Problematik, die wir gestern erläutert.
Also. I'm sorry.
Achso, dann machen wir jetzt das quasi da.
Oder? Also ihr wolltet eine.
Ja, wir wollten mit 2.
Also nur Sie nur einen.
Also auf dem, aber ich kann das ja nachher noch mal geben dann.
Okay.
Ne? Das kann man dazu spielen eigentlich. Ne? No problem. Oh, okay. So this is our fantastic Shiny applications. So you can see it only consists of a couple of buttons on input fields. Essentially, the only thing you can do is press a button and then wait for the response of the service. Maybe Thomas, you already have the lock on your box? This doesn't work anymore? Yeah, but I can switch afterwards, right? So I can re-enable you. Hmm? Huh?
Is this the?
This is really complex.
Ist das vertauscht?
Gut, die probieren nochmal. Ja, schaut besser aus, Thomas. Das ist jetzt wieder auf Image. Naja, das haben wir, ich weiß nicht, das war total schwierig.
Das Kabel von ihm nicht. Lass das? Das lassen.
Ja.
Einfach nur das Kabel und dann wieder von dort darüber. Nicht den Switch.
Aber also.
Bitte? Genau. Geht das? Weil dann ist am Screencast.
Was willst du machen? Ich stecke mich wo an? Und was mache ich denn? Und woran steckst du dann? So what? Yeah, so so we make just one little click here. For example, I go directly. You don't see anything. Oh. Achso, und jetzt haben wir natürlich wieder die Geschichte. Ja. Nicht, weil es ein Linux-PC ist. Hallo? Nein, das gibt's ja nicht.
This is Linux. Welcome to Linux. That works. Nein, also da haben wir jetzt nichts geändert. Also wir haben jetzt nur
This is this black magic box.
Okay, in any case, we just switch over to yours, right? For the logs, and then we play. It worked before, right?
Yeah, so
for whatever reason this doesn't work.
yeah, it's also a bit dependent on this project.
Okay, now we see his screen.
Yeah, and
yours?
if I have to switch here, that's the problem. Okay, so anyway, we press model train, and as I explained in the background, this REST call to the server, and so the training is devised such that it takes a couple of seconds, so that we do produce a bit of CPU, and what you can see here is more or less a confusion matrix of a binary classification that we used for the test data. And what we can have a look here is at maybe at the log files. Okay, maybe in the meantime, while this still collects the logs, maybe my connection is lost here. What we also would like to show you is that we change something in the application and we deploy that. So this is a tad slow at the moment. So maybe remember that here we have the words crisp console, and I will change the source code a bit so that we have console meetup or something, and we can then watch the pipeline being triggered and deploying the new application. So I go here to RStudio. I call this here now maybe live, and save that. Press the commit button. Oh, too early. So I should stage this one for pushing it back to the repository. I call this meetup live, the commit message. There is only two things. One thing I changed. So this is this line of code here. I press commit. This is more or less done. And the other thing I have to do is push it back to the repository. And Thomas, are you ready to watch the? Oh yeah, very good. So I now pushed it up to the repository, and just by committing pushing the commit up to the repository, the pipeline should be triggered, and hopefully now you have Thomas. Thomas, du müsstest die dann ein bisschen auf Mira schalten. Ja. No, this is a Tecton pipeline. So there is two possibilities to initiate a pipeline on the IBM cloud. It's being triggered by GitLab, and then you have the option of taking the standard tool chain, as it's called. And the option is that you instantiate your own tool chain. Thomas has set up something using the Tecton tool chain. This is something that emerges out of the Cloud Native Computing Foundation. So this is the foundation that promotes Kubernetes and promotes Prometheus, for example, for system monitoring of Kubernetes. But maybe we can still see it in work here. So before it's gone, you can see the pipeline running here. First line, so I had to do nothing. Yes, I'm just a developer. I write the commit, it pushes it to the repository, and that triggers the deployment pipeline and the GitLab action, yes. Yeah, please, Thomas, instruct me. Where's the source code, Thomas? Where's the link to the source code? Where is it? Yeah, this one. Okay, so this is my commit message. So immediately I see on this nice pipeline here the commit message that actually triggered the deployment. And if I click on that one, fantastically, I'm right in the GitLab repository, and I can see the source code that I changed that triggered this commit. So this is, I would say, Yes. So there's a couple of possibilities that you can trigger. Yeah. Yes, of course, I would not do that in a real scenario, because usually we would have a user story task. Yes, thank you for pointing out. Yes. So usually one would have a user story task. That usual story task would automatically create a branch. I would sit on that branch. I would work on the branch. I would commit as many times as I want. Then I merge that branch back to master, whatever I'm working on, usually develop, of course. And that in a real scenario would then, and so forth. So, but yes, thank you for pointing out this, of course, is nothing that you will ever want to do in a real project. But it's just for a quick check. So yeah, this was the demonstration of the pipeline, and we're very late already. So I will just try to start the load test very quickly. So the fantastic thing for a load tester is if you can start the load tester with one command line, with a single line of a command. You don't have to do anything. You can schedule the load test for midnight when you're already in bed, and you will have the results next morning when you come to office. And you can use all the system resources because they're not taken up during because they are taken up during daytime. So how that essentially works, we have a look at, wrong window, at the response time. So we have here a custom-made Grafana dashboard, very, very simple, the most primitive you can think of. The one is the Plumber response time, the other is the response time as seen by the load testing client. And what I will do now is start a load test, and starting a load test essentially means instantiating a Kubernetes cluster job that instantiates the K6 image container. So the container contains the load test. The first thing that the container does when it's being started up, it invokes the entry point, as some of you may know, defined in the Docker image, and that essentially starts the load test. So what we do now is have a look at the definition of the load test. Essentially, I pass a couple of arguments to the invocation, to the arguments that run the actual load test. Here I say one virtual user and last for 60 seconds, and invoke the training stuff. Yeah, so what we had just before on the screen, that will be invoked. And now we make a kubectl apply -f job file. And this command starts this container on the platform, hopefully. Hey. So you always have to delete the previous one first. Thank you. So because the pods, once they are run, they're being made immutable, so they remain there, but they can't do anything because they're defined as run only once. So they're more or less a dead body, but you can't have two dead bodies in one place. So this is why we have removed the old one. Yeah, and by the way, then of course we have to switch over to a load test environment. We should be seeing a couple of points here. In the meantime, maybe we look at our log files. Oh, they're still searching. Wait. The mic's on. So we try to reload that one. Yeah, I think we call it a day. Seems like this has been working so many times before, but in front of the audience. It's unfortunately another strike of Murphy's Law. I don't understand. Yeah, we don't see any CPU consumption here, so quite weird. Yeah, okay.
Question from the audience.
Yeah.
Why this is already trying to answer.
Yeah, but this is the dots that I created manually. More or less. This will be part of the. This will be the topic of the second talk today.
I'm sorry. Okay. I think we're allowed to end the nice presentation because we saw the first.
Yeah, thank you. Thank you. Mario, you're so kind.
Are there any other questions for the idea? Questions?
Okay, perfect. Yeah, so from my side, a part, of course, of this for this demo that has not worked out the way it should, because I thought it would be the ice on the cake of today's presentation, to show you that you can more or less with a one-liner invoke all the functions that we've implemented. You could see how the pipeline would be working. And oh, by the way, the pipeline, maybe I'm allowed to one more switch back. And you have here the live, just to make sure that we actually have deployed a new version of the application, at least that worked out as it should.
One question. How big is the active part of the work?
No, because Mario just also wants to talk a bit. So sorry for that.
So please questions
After Mario's talk.
But we need to do some technical, adjustments for our interesting setup here. So in the meantime, I would say 10 minutes break. Please grab a drink, use the bathrooms, and then we start fresh with the talk about RStudio Connect and qubits.